This is going to be a lesson on calculating limits using limit laws. So before you start, we do assume that you've already covered the introduction to the tangent problem, the introduction to the velocity problem, and taken a look at numerical and graphical limits already. This is a kind of a continuation of that discussion. But limit laws, what they're going to allow us to do is to take away one of the major drawbacks from numerical and graphical limits, which is the fact that they're estimates or guesses. What the limit laws are going to allow us to do is to exactly calculate these with no guessing. So this is sometimes referred to as doing these algebraically as well, using manipulation, but you're using the limit laws to do these. So the limit laws, first we're just going to spell out what they are, and then we'll show you how to actually use them. So start off by assuming that the limit as x approaches a on f of x and the limit as x approaches a on g of x exist. So the left and the right hand limits agree, the limits exist, and assume that c is a constant. Then the following must be true. 1. The limit as x approaches a on f of x plus g of x is equal to the limit as x approaches a on f of x plus the limit as x approaches a on g of x. So basically the difference between the left-hand side and the right-hand side of this law. According to the left-hand side, what you're attempting to do is find the limit of two functions that are being added together. But by order of operations, in theory, what you should have to do is add these two functions together first and then calculate their limit. Well, if you think about it, I don't even have to make them very ugly functions. Let's just say I give you this one, and we add it to the square root of x minus 7 plus x squared over, I don't know, x squared plus 3x minus 10 kind of deal. Even if I just ask you to add these two functions together, it's already a complicated problem. You've got to get a common denominator, you've got to combine like terms, all kinds of interesting things happen when you try to add these together. It's doable, but it's challenging. Instead, according to this limit law, what you can do is take each limit individually. And remember, assuming these limits exist, these limits are equal to numbers. So on the right-hand side, instead of adding the two functions, what you're adding are the two numbers. Numbers are almost always easier to add than functions. So that's your first limit law. The second limit law says basically the same idea, only instead of adding the two functions, you're subtracting. On the left side, we are subtracting the functions first, then taking their limit, whereas on the right side, we're taking the two limits, finding their value, and subtracting the numbers instead. Okay, so the sum of the limits is equal to the limit of the sums, essentially, or differences. Number 3 allows us to take this c, remember c is a constant, so this is taking the limit as x approaches a on a constant times a function, and instead pulling that constant out and then taking the limit of the function without it and then multiplying that times the constant. The fourth limit law is that the limit as x approaches a on f of x times g of x is equal to the limit as x approaches a on f of x times the limit as x approaches a on g of x. So instead of multiplying the two functions and then taking the limit, you can take each limit individually, coming up with a number, and then multiply the numbers. The other way to say this is that limits can be split across addition by number 1, across subtraction by number 2, across multiplication by number 4, and then number 5 is going to allow us to split limits across division. The limit as x approaches a of a quotient, you can take the limit of the numerator separate from the limit of the denominator. As long as, you got to be a little careful when you start putting denominators on things though, the limit as x approaches a on g of x, which is in your denominator, cannot be equal to 0. Clearly that will give you a 0 in your denominator, which is a big no-no. Notice this doesn't say g of x equals 0, because if g of x equals 0, you're out of luck anyway, because you would have already had a function of 0 in your denominator. This is saying that the limit on g of x as x approaches a can't be 0. The next set. Number 6 says the limit as x approaches a on a function raised to an nth power is equal to the limit as x approaches a of the function that limit of the function raised to the same power. And again, the difference between the left side and the right side. According to the left side, if you want to take a limit of, let's say, I don't know, x squared plus 5x minus 3, and you raise it to the 10th power, according to that left side, you would have to raise this to the 10th power first. And remember, that's not simple. It's not raising each one of these to the 10th power. That's x squared plus 5x minus 3 times itself 10 times. That's a lot of multiplication. You don't want to have to do that. So according to the limit laws, what you can do instead is just take the limit of the function inside, find the number for that limit, and then raise the number to the 10th power, which is pretty much always going to be easier than raising the entire function to that power. Okay. So let's take a look at the next one. The limit as x approaches a on c equals c. We can kind of give a geometric argument for this. If you take the limit as x approaches a on c, so c is your function, and remember c is a constant. Well, what does the graph of a constant function look like? It's a horizontal line. The graph of a constant function is a horizontal line, y equals c. Well, you can pick any x value you want. If this is a horizontal line, then as x approaches a, the only y value you're ever going to get on this thing is c. So in English, what we say is that the limit of a constant is that constant. The next one says that the limit as x approaches a on x to some power is equal to a to that power. So in other words, if you have the limit as x approaches a on, this is just a monomial at the moment, it's x raised to some power, you can instead just take that number a and put it in place of x and take a to the n instead. Similarly, if you have the limit as x approaches a on the nth root of x, you can instead put in a in place of x, put in the number. Now this is what happens if these are just x's. If we have an entire function under that radical, meaning it's not just x, it's a whole function, now you got to change it up just a little bit. You can't directly substitute a necessarily in place of f of x, but what you can do is move your limit symbol under the nth root. A lot of times this will be a square root, but it's not exclusive to that. This could be a cube root or a fifth root, whatever it happens to be. So you can move the limit under the radical. Let's go ahead and take a look at some examples. Let's go ahead and look at use limit laws to evaluate the limit as t approaches 2 on t plus 5 over 3t. So limit laws. So we know, for example, this is a quotient, that we can take the limit of the numerator, so this is the limit as t approaches 2, of the numerator, which is t plus 5, divided by the limit of the denominator, so the limit as t approaches 2 on 3t. We also know that we can, for example, split this limit across addition and pull the 3 out as a constant in front. So the numerator can be the limit as t approaches 2 on t plus the limit as t approaches 2 on 5. And in the denominator, I'll have 3 times the limit as t approaches 2 on t. So according to the limit laws, all of these are legal. And then we know that the limit as t approaches 2, because this is just a t, I can go ahead and directly substitute 2 in place of t. Technically this is t to the 1, so this would be 2 to the 1. And then for the next one, the limit as t approaches 2 on 5. Remember, the limit of a constant is that constant, so that's 5. In the denominator, we pulled the constant out front, so that stays there. And then the same replacement that we did up here in the numerator, I'll do it again. Since this is just t, which is t to the first power, I can plug in 2, or 2 to the first power. So in other words, this becomes 2 plus 5, also known as 7, divided by 3 times 2, also known as 6. So this limit is equal to 7/6. And the important thing about this is not a guess. This is not an estimate. We didn't have to look at, putting in numbers as they approach 2, like 1.9 and 1.99 and 2.1, etc. We don't guess off of this. This is the exact value of this particular limit. Let's look at another example. We're going to use limit laws to evaluate the limit as x approaches -1 on 4x cubed minus 2x squared. So we can, for example, split this across subtraction. We can also pull those constants out front. So this will be the limit as x approaches -1. Pull the 4 out front. So 4 times that limit on x cubed minus 2 times the limit as x approaches -1 on x squared. So now each one of these limits is x to some power. This is that x to the n, which means since it's just x to the power, we can go ahead and replace -1 in place of x. So this becomes 4 times -1 cubed minus 2 times -1 squared. And -1 cubed is still -1, so this is -4, minus, and then 2 times -1 squared is +1, so this is 2 times 1 for 2. So it's -4 minus 2, also known as -6. So again, that's an exact value for this limit. So just a thing to note, I am applying the limit laws step by step. But in practice, honestly, we take these for granted and we skip these intermediate steps. Notice something that kind of starts to become a pattern here. Instead of asking you to calculate this limit, what if I had said, hey, I have a function, f of t, and that f of t is t plus 5 over 3t. Please find me f of 2. What would you have done? You would have plugged in 2 in place of t and then simplified, and guess what you would have gotten? Notice they match. That's exactly what we did. 2 plus 5, 3 times 2. Same thing here. In this case, if I had said, hey, I have a function f of x, and it's 4x cubed minus 2x squared, please tell me what you would get for f of -1. You would have taken 4 times -1 cubed minus 2 times -1 squared, and guess what? You would have gotten -6. So in some cases, this does not always work, but in some cases, instead of writing out every single limit law, you can just do what's called direct substitution. Now the direct substitution property, it's a result of these limit laws. As a result of the limit laws, if f is a polynomial or a rational function, so this only applies in those cases, which in case you don't remember, polynomials, what you're looking for are functions in which all of your powers on your exponents are nice, pretty, positive, whole numbers. If you have an exponent that's negative or an exponent that's a fraction, you're not looking at a polynomial. Rational functions are the ratio, or numerator and denominator, of two polynomials. Okay, so that's what we're talking about. This one's polynomial, this one's rational. So in those cases where you're either looking at a polynomial or a rational function, and a is in the domain of f, so this is assuming a is in your domain, then the limit as x approaches a on f of x equals f of a. In other words, if you want to calculate the limit as x gets close to a, all you have to do is take the function and plug a in. Now, this is kind of a sticky point for some of these. A has to be in the domain of your function. Okay, so for example, go back to this one. The 4x cubed minus 2x squared as a function is not a problem because that particular function is a polynomial. What's the domain of every polynomial? It doesn't matter whether it's a cubic, a quadratic, a linear. As long as it's a polynomial, its domain is all real numbers. What's the domain of a rational function? That one's a little less straightforward, but not by much. The domain of a rational function is also all real numbers except you can't let in any number into the domain that's going to make your denominator 0. So in other words, if you want the domain of f of t equals t plus 5 divided by 3t, you can plug in any t value you want as long as it's not t equals 0. So usually we can write that as, it depends. Interval notation, union 0 to infinity. You can also write it as the set of all t as such that t isn't 0. Okay, so that's typically how you see these written. So direct substitution is a fantastic property to use as long as your function is either a polynomial or a rational function and that a is in the domain of those functions. So a couple things to keep an eye on. Direct substitution does not apply to rational functions that result in a 0 in the denominator, because if it gives you a 0 in the denominator, a is not in the domain of your function. Also, the limits have to exist in the first place in order to use any of the limit laws, and therefore direct substitution. Direct substitution comes from the limit laws. If you remember, if the limits don't exist, you don't get to use the limit laws, which means if the limits don't exist, you don't get to use direct substitution. Usually the example I like to give for this is if you have something like, we'll actually look at this later, the limit as x approaches 0 on x squared sine 1 over x. We'll take a look at how to deal with this later. It's going to require a lot more thought, but initially students like to try direct substitution and say, okay, well that's 0 from the limit as x approaches 0 on x squared times, if you take the limit as x approaches 0 of sine 1 over x, notice you're going to get a 0 in the denominator. Well, that doesn't exist. Not really. You can start talking about infinity and negative infinity, but remember, technically infinite limits don't exist. But so 0 times does not exist is not 0. It means you couldn't split this across multiplication to begin with. This requires a completely different approach, which we'll take a look at. So what do we do if direct substitution doesn't work? In all honesty, most limits are not going to be able to be done by direct substitution. That would be too easy. So what do we do when it doesn't work? For example, if we were asked to find the limit as x approaches 1 on x squared minus 1 over x minus 1. If we tried direct substitution, notice what we'd get is 1 squared minus 1 over 1 minus 1, which is 0 over 0. So not only do you get a 0 in the denominator, which means 1 is out of the domain of this function, so that's a no-no, you also get that 0 over 0. And hopefully you've already taken a look at the fact, I've got some extra notes for this, but this is what we call an indeterminate form. Okay, 0 divided by 0 is very strange. It's a weird exception to all the rules that you think you know. 0 divided by 0 isn't 1, it isn't 0, it isn't undefined. 0 divided by 0 is something that we can't determine in its current form. We need to change that form if at all possible. So if you notice when we look at this, we come up with the indeterminate form. Let's try some simplification. If you take a look, you see the x squared minus 1? Hopefully, that kind of leads you towards the fact that that can factor. X squared minus 1 is the difference of two squares. So it's x plus 1 over x minus 1 over x minus 1. Now notice something. See how you've got x minus 1s in both the numerator and the denominator? So when you cancel these, you get the limit as x approaches 1 on x plus 1. Now, these two functions are not the same if you take off that limit sign. If you look at x plus 1 times x minus 1 over x minus 1 and say that that's equal to x plus 1, you're actually incorrect. These two cannot be equal, because what number are you not allowed to plug in for x on the left-hand side? Take a look at the denominator. You clearly cannot plug in x equals 1. But if you say that it's equal to just plain old x plus 1, does this have any domain restrictions on the right side? No, you can plug in anything you want. So what you got to keep an eye on is the only way these two things are equal is if you add in this little x can't be 1. Now they are equal. Now we don't have to worry about that with the limits, because remember, by definition of a limit, limits are about what happened near your a value, meaning near 1 in this case, not about what happens at 1. So we're going to be able to work around that a little bit just based on the definition of the limits themselves. So let's go ahead and continue our problem. So we're looking at the limit as x approaches 1 on x plus 1. Notice x plus 1. What kind of function is that? It is linear, but remember, all lines are also polynomials. So polynomials, by definition, we can use direct substitution. So now that we've simplified this, now we can direct substitute all we want. And sure enough, that limit's going to be equal to 2. Now this should look familiar if you have already gone over the introduction to the tangent problem, because if you remember, this is the limit that we got. We didn't call it a limit, but this is what we got when we were trying to find slopes of secant lines. So these were the slopes between the ordered pair 1, 1, and then the function was x squared. This was finding the slope of the tangent line to the curve x squared at 1, 1 was the problem we looked at. And that was our y value minus our y value over our x value minus our x value. These were the slopes of our secant lines. And that's the limit that we actually just took a look at. Let's take a look at another one. Examples of factoring or expanding. We just did one where we had to factor. Let's take a look at this one. Find the limit as h approaches 0 on 4 plus h squared minus 16 all over h. Notice if you want to try direct substitution first, if you put in 0, you're going to get 4 plus 0, which is 4. So you're going to get 16 minus 16 in the numerator, and you're going to get 0 in the denominator, which makes it, again, the indeterminate form 0 over 0. You cannot calculate this limit until you change the way it looks. Well, this one we can't really, we could try factoring, but what we'll need is to be able to cancel out this h, and the factoring of the numerator isn't going to help us with that. So let's go ahead and try some expansion, see what happens. So we get the limit as h approaches 0. When you expand 4 plus h squared, please keep in mind that's a FOIL. That's not 16 plus h squared. You can't just square the 4, square the h. It's 4 plus h times another 4 plus h, which means it's 16 plus 8h plus h squared. Now minus 16 all over h. And notice, so we have 16 minus 16 in your numerator, and the two terms that you have remaining in your numerator have an h in common. And because of that, you can go ahead and factor it out. So you get h times 8 plus h over h, which allows me to very nicely cancel out those h's. So I get the limit as h approaches 0 on 8 plus h. Now notice, this is again, it's a polynomial. Now I can directly substitute. Polynomials and rationals I can directly substitute as long as it's in the domain. So this becomes 8 plus 0, also known as 8. So this limit is equal to 8. Now what I want you to keep a very close eye on, because this is going to be a part of your calculus grading experience, watch your notation. See how I have a limit sign here and here and here? What step did I take between this step and this step that allowed me to drop out my limit? I directly substituted. I used the direct substitution property that, assuming you're looking at a polynomial or a rational and a is in the domain, that the limit as x approaches a on f of x equals f of a. Okay? Notice the left side has a limit, the right side doesn't. This is direct substitution. Only once you direct sub are you allowed to drop that limit. You cannot write this entire problem down without the limit sign in front, or you're going to lose points for that. Because think about it, if you leave out the limit all the way, and you get to this point, and you're doing this, and you do this, and then you cancel, and you're left with this, and then you do this, and then you do this. And notice I dropped out my limit sign, so let me make sure I write wrong on this so nobody does this. It's this step that's really going to kill you right here. You just told me that 8 plus h is the same as 8 plus 0. Not last time I checked, it's not. They're only equal if h is equal to 0. So you cannot drop out that limit until you directly substitute. Okay, let's take a look at another example. Evaluate the limit as a approaches 0 on the square root of 9 plus a minus 3 all over a. Even if you could directly substitute for this, And technically, according to our direct substitution rule that we have at the moment, you can't because it's got a radical. A radical means this is not technically a rational function. But if you could, for the moment, let's say you could, you'd get 9 plus 0, so this would be the square root of 9, which is 3. You'd get 3 minus 3, you'd get 0 over 0. So again, we're back to the idea of an indeterminate form. So whenever you have a limit and you need to simplify and it contains a radical, you need to start thinking conjugates. It may be unfamiliar the first time you take a look at a problem like this, but conjugates is the technique you want to use. This is technically rationalizing your numerator instead of rationalizing your denominator. It goes back to this idea. When we had 1 over the square root of 2, for example, you'd multiply square root of 2 and square root of 2, multiplication by 1, you get square root of 2 over 2. That's rationalizing your denominator. Whereas if you have 1 over 1 plus the square root of 2, you can't multiply by the square root of 2 over square root of 2. You got to multiply by 1 minus square root of 2 in order to rationalize this. Same deal. We are going to take the limit as a approaches 0 on the square root of 9 plus a minus 3 over a, and we're going to multiply it by its conjugate, which is the square root of 9 plus a plus 3. Top and bottom. This is what we call multiplication by a well-chosen 1, meaning I just multiplied by 1. It's the same in the numerator and denominator, so that's 1, but I chose how I wanted to write that 1 to make my life better. So I'm going to look at the limit as a approaches 0, and I'm going to do some multiplication. You got a FOIL up here in the numerator. So your firsts are the square root of 9 plus a times the square root of 9 plus a, also known as 9 plus a. Then we'll have plus 3 times the square root of 9 plus a, and then minus 3 times the square root of 9 plus a, and then minus 3 times 3, so minus 9, over. In my denominator, technically you could distribute and take a times the radical and a times 3, but believe it or not, you don't want to. Because the goal is to have everything factored in the hopes that we can get some things canceled. And if you distribute, basically you just made it so that you would have to factor it back out in order to cancel. So take a look at some nice things that happen in our numerator. It looks like a mess when you first start, but notice you get positive 9 and negative 9, plus 3 times the radical, minus 3 times the radical. So all you're left with in your numerator is a. But notice because I didn't distribute, you can see it right away. This a cancels this a. So in your numerator, you're left with nothing, so you're left with 1. And then in your denominator, you're left with the square root of 9 plus a plus 3. And from here, we can go ahead and apply some of those limit laws. We get the limit as a approaches 0 of 1 over, now I can move the limit under that radical, the limit as a approaches 0 on 9 plus a. So I moved it under the radical, and then I'll split this one across addition. Limit as a approaches 0 on 3. So the limit on the constants are the constants, so the numerator stays 1. The denominator, we get a plus 3 here. And down here, we get the limit as a approaches 0 on 9 plus a. That's a polynomial, so that's eligible for direct substitution. So under our square root, we have 9 plus 0. So when we do all the simplification, we get 1 over, the square root of 9 is 3, plus another 3 is 6. So this limit is exactly equal to 1/6. No guessing, no estimation. That's its exact value. Let's take a look at another one. We're trying to take a look at all the different kinds of curveballs you can get thrown with these. This is a limit in where you're asked to find the limit as x approaches -4 of 1/4 plus 1 over x plus 4. This involves what we refer to as a complex fraction, and complex fraction just means you've got fractions within fractions. So this is one large fraction, but it's got fractions in its numerator in this particular case. Okay. If you try direct substitution, you're going to get a 1/4. When you plug in -4 in place of x, you're going to get a -1/4. And notice immediately You get 0 over 0. You're back to indeterminate form on this one again. So we need to find another way to work with it. So what we do is we keep this in mind. The goal with complex fractions is always the same. We take a over b and c over d. This is what we want to aim for. If we can get one fraction in the numerator and one fraction in the denominator, we can use the property that says instead of dividing fractions, we can multiply by the conjugate of the denominator, essentially getting rid of the division and turning it into multiplication. The trick is you can't use this property until you have one fraction in the numerator and one fraction in the denominator, which we do not currently have. The denominator's fine. That's technically x plus 4 over 1. Your numerator's not okay. You've got two fractions. So we actually need to go ahead and add those together before we can turn this into multiplication. So you have 1/4 plus 1 over x. Common denominator between those is going to be 4x. So you multiply the first fraction by x over x, the second fraction by 4 over 4. This will give you 4x in both denominators. So you get x over 4x plus 4 over 4x. In other words, you get x plus 4 over 4x over x plus 4, technically over 1. Now we have one fraction on top and one fraction on the bottom. So we can go ahead and change this from division to multiplication by the reciprocal of the denominator. That's plus 4. And notice something very nice happens for us. There go the x plus 4's. So we're now looking at the limit as x approaches -4 on 1 over 4x, which is a rational function. The only number out of the domain of this rational function is 0, which means we can directly substitute -4 in there. So that's 1 over 4 times -4, which is -1/16. And that's the value of this limit. We need to discuss what happens when we want to take the limit of a piecewise defined function. So if your pieces are individually polynomials or rationals, great. Direct substitution is still an option. You want to use that if that's actually possible. If direct substitution is not possible for a piecewise function, we're going to need to examine the limit from the left-hand side and the limit of the right-hand side separately. And let me see if I can illustrate what I'm talking about here. When you graph piecewise functions, usually one of two things happens. Either you graph your first piece and, let's say it's an open circle, and then you graph your second piece and it starts here and you get, some other kind of function going on. That's one option when you look at the graph of a piecewise function. One of the other options, this is certainly not an exhaustive list, but one of the other things that can happen is you graph the first half of your function, right? And you get an open circle here. And then you start to graph the second half, and it turns out that the second half shares this ordered pair, and it ends up closing your circle. Okay? Well, notice if this is where I'm looking for the limit at a. In the first example, the limit from the left as x approaches a on the function versus the limit as x approaches a from the right on the function do not match. The limit overall does not exist. But in the second one, it does. The left-hand limit and the right-hand limit agree at a, so the limit overall does in fact exist. Now the good news is if you're looking to calculate the limit anywhere else except a, just use direct substitution. Let's say you were trying to calculate the limit here at b. Well, this limit here is the same from the right and the left. You just direct substitute that number in. That would be ideal. Unfortunately, it pretty much never works out that way. So let's take a look at an example. Evaluate the limit as x approaches 1 on the function for f of x equals x squared plus 1 if x is less than 1, and x minus 2 quantity squared if x is greater than or equal to 1. So notice we're looking for the limit at 1, and of course that's where this is changing. So we don't know if we were to look at this, would we get the same limit from the left as we do from the right, or would we get different limits from the left and the right? We don't know. So we're going to algebraically look at that. So we're going to look at the limit as x approaches 1. Let's start with from the left. We're going to do both. It doesn't matter which one we do first. So remember what that means. It means you're coming at 1, your x values are coming at 1 from numbers smaller than 1. So when you're looking at a piecewise function, which one of these pieces do you use when you're using x values smaller than 1? It would be this piece, x is less than 1. So in the case where you know your x values are smaller than 1, the function you're working with is the first piece, x squared plus 1. Well, notice that's a polynomial, which means you can directly substitute 1 squared plus 1. You're going to get 2. So the limit from the left at 1 is 2. If we look at the limit from the right, the limit as x approaches 1 from the right on f of x, now we're coming at 1 from numbers larger than 1. So x is greater than or equal to 1. This is the piece we'll use. Well, in that case, our function is determined by x minus 2 squared, which again, is a polynomial, so you're eligible for direct substitution. So that's 1 minus 2 squared. That's negative 1 squared, also known as 1. Do your left limit and your right limit match? No. So therefore, the limit as x approaches 1 on this function does not exist, since the limit as x approached 1 from the left on my function did not match the limit as x approached 1 from the right on my function. If we take a look at a graph of that particular piecewise function, notice the change occurs at x equals 1. When x is less than 1, we go ahead and get that graph of x squared plus 1. That's our basic shape parabola shifted vertically up by 1. And if x is greater than 1, we get x minus 2 quantity squared, which is the parabola with everything shifted 2 to the right. So this is what it looks like, and sure enough, as you approach 1 from the left, you go up here to 2, and as you approach 1 from the right, you go here to 1. Feel free to use graphs of piecewise functions to verify that your answer is correct, but you don't want to use them to actually get your answer. The way to actually verify that you're going to be able to get the correct limit is to do these algebraically or using limit laws. Let's take a look at another example. Let's evaluate the limit as x approaches 4 on g of x for g of x equals the square root of x minus 4 if x is greater than 4, and 8 minus 2x if x is less than 4. Notice for this one, x isn't even defined for x equals 4. But remember, limits aren't about what happens at the number, they're about what happens near the number. So we actually don't need this function to exist at x equals 4. So x equals 4 is where we have the change from one piece of this function to the other. So we are going to have to look at the limit as x approaches 4 from both the left and the right. So if we look at the limit as x approaches 4 from the left, in other words, we need to look at this as x approaches 4 from numbers smaller than 4. Which of the two pieces should we use? Notice this is where x is less than 4, so we're going to use 8 minus 2x. And again, that's a polynomial, so it's eligible for direct substitution. So it's 8 minus 2 times 4, also known as 0. If we look at the limit as x approaches 4 from the right on this function, we have to decide which piece to use. Should be obvious, there's only 2, but just to verify, this is coming at 4 from numbers larger than 4. Well, the first piece is where you have x is larger than 4. So we look at the limit as x approaches 4 from the right, which gives us the square root of x minus 4. Technically, at the moment, we can't use direct substitution on this, so we take the square root and we move the limit underneath. So that's the square root of the limit as x approaches 4 from the right on x minus 4. Now that limit is a polynomial and therefore eligible for direct substitution. So when you directly sub in, you get 4 minus 4 under your square root, which gets you the square root of 0, which is 0. So notice in this case, the left-hand limit and the right-hand limit agree. So therefore, the limit as x approaches 4 on f of x equals 0. Since the limit as x approached 4 from the left on the function was the same as the limit as x approached 4 from the right on the function, and they were both equal to 0. If we want to take a look at the graph of this just to verify our answer, here is for x greater than 4. There's your square root of x minus 4. That's your basic shape square root graph shifted by 4 to the right. And then here is the other part, the line, 8 minus 2x, which has a slope of -2 and a y-intercept of 8. And notice, as x approached 4, they do in fact have the same limit. They both approach 0 as you approach 4 from both the left and from the right. What happens when we're trying to do a limit that involves an absolute value? For example, evaluate the limit as x approaches 0 of the absolute value of x over x. If you could use direct substitution on this, which technically, again, you can't because the absolute value of x is not a polynomial, even if you could, you'd still get 0 over 0. You'd get your indeterminate form. So now what is it you're supposed to do to simplify this? I mean, remember, indeterminate means we need to be able to change how it looks if we want an exact value for this limit. Well, the technique for simplifying an absolute value limit isn't simplifying at all. It's using the piecewise definition of absolute value. And in case you don't remember, the piecewise definition of absolute value of x equals x if x is greater than or equal to 0, and it's equal to the opposite of x if x is less than 0. This is what absolute value means. So believe it or not, when you're dealing with an absolute value in a limit, you deal with it as you would any other piecewise function, which is what we just did in the last two examples. So we need to split this and look at what happens when you're on the left of 0 versus what happens when you're on the right of 0, because that's where we're looking to take our limit. So let's look at the limit. Let's start with the right one. The limit as x approaches 0 from the right on the absolute value of x over x. Now, when you're looking at the limit as x approaches 0 from the right, that means x is approaching 0 from numbers larger than 0. So which one of these pieces do you use for x values larger than 0? You use the top one. So the absolute value of x is the same thing as x as long as your x was positive to begin with, which it is in this for the right-hand limit. So this is x over x. Well, at first glance, that doesn't help us. It's still indeterminate form of 0 over 0. So simplify again. Notice it's the same factor on top and bottom. They cancel and leave us with 1. And the limit of a constant is the constant. So the limit as x approaches 0 from the right on the absolute value of x over x is 1. If we look at the left-hand limit, take a look at the limit as x approaches 0 from the left on the absolute value of x over x. If we use the piecewise definition, as we approach 0 from the left, that means we're coming at 0 from numbers smaller than 0. That's the bottom piece. X is smaller than 0, or less than. So in those cases, absolute value of x is actually equal to the opposite of x. So again, when we go ahead and simplify this time, when we take negative x divided by x, we don't get 1, we get -1. But it's still a constant, and the limit of that constant is the constant, so it's -1. Notice there's a disagreement between the left and the right-hand limit. So therefore, the limit as x approaches 0 on the absolute value of x over x, it doesn't exist, since the limit as x approached 0 from the right on the function was not equal to the limit as x approached 0 from the left. So that's how you deal with absolute value limits. So let's take a look at what happens when we have a limit that is an infinite limit, but it's not an indeterminate form. What I mean by that is, let's evaluate the limit as x approaches 5 of x squared minus 5x plus 6 over x minus 5. So notice if you try direct substitution, you're about to get a 0 in your denominator, which means automatically direct substitution is not going to work. Limit laws do not apply for this limit. But we can kind of keep an eye on that numerator. Notice when we put in 5 directly in for x, we get 25 minus 25 plus 6, which leaves us with 6. So this is not an indeterminate form. What we have is the numerator approaching a constant and the denominator approaching 0. So while we cannot apply the limit laws, and technically this limit does not exist, period, we might be able to glean a little bit more information if we take a look at this a little bit more intuitively. Notice that your numerator approaches 6 as the denominator approaches 0. At x equals 5, because of this x minus 5, what do you expect to have if you were to look at the graph of this at exactly x equals 5? What do you expect to see? You should expect to see a vertical asymptote, which is how we're probably going to get either an infinity or a negative infinity as we tend to look at these limits. So I want to take a look at this using what I refer to as the intuitive approach. And this is going to be especially helpful for those of you who plan on continuing on to a Calculus 2 class, because you will do these kinds of calculations many, many times. We'll do them in Calc 1 quite a bit, but in Calc 2 you do them even more. So the more intuitive you can get in your approach to these, the better off you're going to be as far as speed on these calculations. So what do I mean by an intuitive approach? Because this is an infinite limit, we need to approach the left and the right differently, because we're not sure, is this going to go to positive infinity or negative infinity from one side and on the other side. So we want to go ahead and look at them separately. Okay. So let's say for the moment, if we were letting x approach 5 from the left, okay, your numerator is approaching 6. Period. It doesn't matter whether you're approaching 5 from the left or the right. You're approaching 6, which is a positive number. Okay, so I'm going to kind of fudge the notation a little bit on this. Approaches 6, and the important thing to keep in mind is that 6 is a positive number. Your denominator, if you're approaching 5, your denominator should be approaching 0. But what I want to concentrate on is approaching 0, but from the positive side or from the negative side. Because whether you divide this positive number by a positive or a negative will change the outcome. So what I mean by that, if you approach 5 from the left, you're coming at 5 from numbers smaller than 5. What happens to x minus 5 if you take a number smaller than 5 and take 5 away from it? You're going to get a very small number, but you're going to get a negatively small number. In other words, plug in 4.9, 4.99. You're getting a number that's extremely small, but a little bit negative. So it approaches 0, but it's negative, which means you've got a constant being divided by a number that's getting smaller and smaller and smaller. And what does that do to a fraction overall? It turns the fraction larger. But it's going to be very, very large, but because the numerator is positive and the denominator is negative, it's going to be negatively large. Let's do the same approach, but this time if x approaches 5 from the right. If x approaches 5 from the right, again, the numerator is going to approach 6. I'm a little less interested in that because 6 is a positive number, period. The denominator, take a look at that though. So again, you're approaching 5 from the right, so you're coming at 5 from numbers larger than 5, so 5.1, 5.01. The difference between that number and 5 is going to be very small, so it's approaching 0. But since you're taking, say, the 5.1 or the 5.01 and subtracting 5 from it, it's approaching 0 from a positive value. So this is still getting smaller and smaller and smaller, but it's positive. So when you take the positive number divided by a positively small number, you don't get negative infinity, you get positive infinity. Now what that means is at this vertical asymptote, as you come at it from your left side, it's going to go to a negative infinity. As you come at it from your right side, it's going to go to a positive infinity, which means you can tell intuitively that this limit overall, not only does it not exist, it does not exist. It doesn't equal infinity, it doesn't equal negative infinity, it just doesn't exist, period. So one of the other topics that we want to talk about is the squeeze theorem. And the squeeze theorem says that if you have a situation that meets the following two conditions, you get to draw a conclusion. The two conditions are f of x has to be less than or equal to g of x, which is less than or equal to h of x, when x is near a except possibly at a, And the limit as x approaches a on f of x is equal to the limit as x approaches a on h of x, which is equal to L. Let's see if we can decipher that a little bit. So in other words, you have three separate functions, f, g, and h. F is smaller than or equal to g, which in turn is smaller than or equal to h. So h is the largest of the three, g is in the middle, f is the smallest. And this is true as long as x is near a, except for maybe at a. Okay, so keep in mind these are functions, and this is f of x. Is f of x an x value, or is f of x a y value generally? F of x is generally a y value. So what you literally have are three functions on top of each other. H is on top, g is in the middle, f is on the bottom for this notation. And the other thing that you know is that the limit as x approaches a on f of x is equal to the limit as x approaches a on h of x, and that's equal to L, meaning it exists and it's finite. That's the limit of the bottom function and the limit of the top function as x gets close to a, except possibly at a. Okay, so in case that's still not clear, let's take a look at a graphical representation of what that means. Here's h of x, which is your top function, g of x, which is your middle function, and f of x, which is your bottom function. And notice it also meets the second condition, which is that as x approaches a on f of x, you get a limit of L. The left and the right meet, the left and the right hand limits match, and they're equal to L. And then the same is true on h. As we approach a from the left and from the right on h, you get L as the limit. So now you want to take a guess as to what the limit as x approaches a on g of x has got to be equal to? It's got to be L. It makes sense, and this is why it's called the squeeze theorem. You literally are taking a function above and a function below and saying that at a, if they meet and have a certain limit, then the one in the middle, it's got to have the same limit as those two. That's squeeze theorem. Let's take a look at an example of how we apply that. Evaluate the limit as x approaches 0 on x squared times the sine of 1 over x. I mentioned this a little bit earlier in the lesson, just to say this was something that you can't use direct substitution for, because if you try, you're going to get a 0 times the sine function. We'll talk about direct substitution with that in a bit, but basically, assuming you could directly substitute, you'd have 0 in a denominator. So that would be dne. And 0 times dne, what do we do with that? You can't use limit laws for that. You couldn't split it across multiplication to begin with. So now what are we supposed to do? Well, this is where squeeze theorem is going to come in for us. Traditionally, we like to use squeeze theorem, not exclusively, but we like to use it when we start dealing with sine and cosine functions, because sine and cosine functions have that really nice property that, this is not sine of 1 over x, this is just plain old sine x, that they are bounded between what two numbers? They're bounded between 1 and -1. And unless you stick a number out here and change their amplitude, they're going to be bounded between -1 and 1. So what we know about the sine of 1 over x is that it's bounded between -1 and 1. Now remember, if we're using squeeze theorem, the first thing we're going to try and establish is that three-part inequality, the f of x, g of x, and h of x. Well, because sine x is bounded between -1 and 1, I've got a real good start on this. Notice this is a three-part inequality. The problem that I'm running into is that that's not what I'm trying to find the limit of. What I'm attempting to find the limit of in this particular problem is the x squared times sine 1 over x. So this isn't what I want in the middle. This isn't my g. My g has an x squared multiplied by it. So how do I turn this into this? Well, I just multiply it by x squared. But this is a three-part inequality, which means whatever you do to the middle, you must also do to the left and to the right. -1 times x squared is -x squared, and 1 times x squared is x squared. So notice I now have a three-part inequality with the function that I'm trying to find the limit of sitting in the middle. Okay, so that's the first requirement. The second requirement is that the two limits, the limits of the functions on the ends, the smallest and the largest, must be the same as x approaches a. Well, in our problem, a is 0. So we need to look, what is the limit as x approaches 0 on negative x squared? Well, that's a polynomial, so you get to directly substitute. It's 0. And what is the limit as x approaches 0 on x squared? Also a polynomial, so you get to directly substitute. So therefore, by Squeeze theorem, the limit as x approaches 0 on x squared times the sine of 1 over x must also equal 0, because I met the first requirement for Squeeze theorem, and these two together give me my second requirement for Squeeze theorem. So this is traditionally how we'll use Squeeze theorem. When you can't find the limit of a function, what you can try to do, one of your options, is to find something that bounds it above and bounds it below and hope that they have the same limit at a, and then you can use Squeeze theorem. In fact, if you take a look at a graph of this, here is positive x squared, here is negative x squared. That's a reflection of the traditional parabola reflected over the x-axis, and the graph of the sine of 1 over x actually looks like this. It comes in and then it starts oscillating. This is one of those infinite oscillations that we took a look at earlier. As this moves in, it actually oscillates many times. Let me zoom that in and we can probably take a look. As you zoom in, you can kind of start to see how many times it's oscillating before it hits it. It's going to keep going. But because you know that positive x squared and negative x squared both meet right here at 0, that means that the sine of 1 over x has to have a limit of 0. Without those, you're not really sure what it's going to approach.